Hello and welcome to Science Talk. I am your host, Jim Massa. In this video, exclusively for my Patreon subscribers, I wish to discuss with you metallic hydrogen. What on Earth, or what in the universe, is metallic hydrogen? Well, to answer this, it's time to take a trip to Jupiter. Below Jupiter's swirling cloud tops, which we can see from Earth, the common element hydrogen exists in a very strange, different state. Paul Sutter is an astrophysicist at Ohio State University and the chief scientist at COSI, C-O-S-I, Science Center. So, we know about solid, we know about liquid, we know about gas, the typical states of matter. And of course now there's plasma, which is ionized gas, and so on. And so we know that if you take water, for example, at room temperature, it's a liquid. As we remove energy from it, the molecules move closer and closer. Although water is more dense, it's at its highest density at 4 degrees C, about 39.2 degrees Fahrenheit. And as it gets cooler and cooler, it does start to expand and becomes ice. So ice is less dense than liquid water, which is why ice floats and why the oceans and the lakes are not a big ice cube from the bottom up. And then on the other side of it, we can impart energy into liquid water, for example, causing the molecules to increase their kinetic energy, move further apart from each other, to the point where they escape into a vapor form. So yes, we have solid, liquid, and gas. Okay? And you can plot what's called a phase diagram, and typically increasing temperature, and then when it's at a plateau is when it's adding energy to go to the next state. But you can make a diagram of each element of its phase, of its different phases. And based on this phase diagram, if you were to apply a specific temperature and pressure to it, pressure is also important, you can then make an educated guess as to what state you'll find it in. And pressure is an important point here, because let's take the hydrothermal vents in the deep ocean. The water that comes out of the vent has been heated from, mantle and core processes. It is superheated water. It is, in some cases, as high as 600, 700 degrees C. But yet, it's not a gas. It comes out as a very superheated hot liquid. Why is that? Because of the immense pressure down at the bottom of the ocean. The pressure keeps it in a liquid state. So we're used to things being at sea level of 14.7 pounds per square inch pressure, thereabouts. On the flip side of it, when people doing high mountaineering, what is going on there? They try to boil water to rehydrate their frozen, dehydrated food. Not frozen, but dehydrated food. But the water boils off at a much, much lower temperature because the pressure, the atmospheric pressure is so much reduced that the water can find its equilibrium state and escape as a gas much sooner. So it's not just temperature but pressure. And there are things, the ideal gas law, I call it the old PIV nerd equation, pressure times volume equals the number of moles times the constant times the temperature in Kelvin. There's Charles' law and Boyle's law. Charles' law it relates temperature effects on gas, and Boyle relates pressure effects on gas. So this phase diagram I mentioned is unique to each element because it depends on the precise atomic molecular arrangement and the interactions that take place. When it comes to hydrogen, well, hydrogen is the simplest element out there. There is one proton surrounded by one electron. You may find isotopes like deuterium, which is one proton plus one neutron. And there's tritium, which is one proton plus two neutrons. But typically what we see is one proton, no neutrons, and an electron buzzing around. Okay? So hydrogen, in addition to forming H2O, dihydrogen oxide, if you really want to have fun with people, just walk out on the street there. There's this chemical called dihydrogen oxide. Should it be banned? You'll be surprised at the results you get. People say, yeah, it's water, folks. But anyway, hydrogen can also form a diatomic molecule, meaning that H2. You get two, just like oxygen can form a diatomic molecule, O2. Nitrogen, N2, diatomic as well. Okay? And because of hydrogen, it is pretty much always a gas. Now, you could trap some hydrogen in a bottle and you could cool it down to about 33 kelvins, which is minus 400 degrees Fahrenheit or minus 240 degrees Celsius. Keep in mind, 0K is absolute zero, where all molecular, all atomic motion ceases. But at 33 Kelvin, hydrogen becomes a liquid. At 14 Kelvin, which is minus 434 degrees Fahrenheit, or minus 259 degrees C, it becomes a solid. So you would think that at the opposite end of the temperature scale, a hot gas of hydrogen would stay a hot gas. That's true as long as the pressure is kept low. But if you have a combination of high temperature, high pressure, hydrogen then behaves very interestingly. Okay? And what do we have in Jupiter? High pressure, lots of high pressure, high temperature. Okay? So deep below the planet's visible surface, this is of Jupiter, pressures, temperature increase extremely dramatically. Gaseous hydrogen slowly gives way to a layer of supercritical, a gas-liquid hybrid. And because it's in this sort of a flux state, it can't really settle into, oh, it's definitely a gas, it's definitely a liquid. It's kind of new territory. Too hot to stay a liquid, but under too much pressure to float freely as a gas. In essence, it's a new state of matter. Go even deeper down Jupiter, and if you thought this was strange, wait. Even in its hybrid state, in a thin layer just beneath the cloud tops, hydrogen is still moving around, kind of bouncing around, as a 2-for-1 diatomic molecule, but at sufficient pressures, let's say 1,000,000 times that of Earth's sea level pressure, you get overwhelming compressions, and then you end up getting into this situation where the electrons themselves are removed. So you get this crazy mix of free hydrogen nuclei, basically protons. Okay? But the electrons have been liberated, but the electrons are not continuing to move about their hydrogen atom. They're moving around freely floating. It's a similar situation with metals. Okay, if we look, for example, some of the alkali metals, what have you, or alkaline earth metals, the electrons are kind of in this sort of, for lack of a better term, a sea of electrons all mingling around, and this is why metals are very good at conducting electricity, because of the state of how the metal is put together. The flow, what's electricity? Flow of electrons can easily move through by following the field lines, the electrical field lines. Well, at this point here, hydrogen is sort of starting to behave like a metal. You can probably run an electrical current there. Now, in this state, however, it's still kind of liquid, so it's not solid as we'd find in the metals I just described, but it is dissociated into component parts. And when we have When this happens at very high temperatures and low pressures, we call this a plasma, ionized gas. Okay? But now we are talking high temperatures, high pressure. So at this point here, this is where it starts to become more of a liquid metallic hydrogen. Okay. Going back to going back to metals, and if you look at the periodic table, most of them are metal. You have metals, you have nonmetals, and you have metalloids, which are compounds that have properties of both metals and nonmetal. They're kind of a transitional, sort of in the towards the right center portion of the periodic table. The metals, however, are hard and shiny. They make for good electrical conductors, as I just tried to indicate. The elements get those properties from the arrangements they make with themselves at normal temperatures and pressures. They link up to form a lattice, and each of the atoms will contribute one or more electrons to the community, if you will, to kind of give you an idea. And these dissociated electrons move about freely. They go from atom to atom. And it's this property that allows it to conduct electricity. So what's the big deal about metallic hydrogen? It's not a typical metal. It's behaving differently. Your usual metals have that lattice that I just described of ions embedded in a sort of a sea or pool of free-floating electrons. Stripped down hydrogen atom is just a single proton, and there's nothing a proton can do to build a lattice. It can't build a lattice to do so. When you squeeze on a bar of metal, you're trying to force the interlocking ions closer together, and that's not going to likely to happen. Electrostatic repulsion forces any attempted further squeezing away. Electrostatic repulsion gives the metal the support it needs to be strong. Okay? How many times you take an iron cylinder and you do a stress test on it? You want to see at what pressure, when you squeeze it, will the thing break? And usually it's an extremely high pressure. So then how can the liquid metallic hydrogen that's found inside Jupiter, how can it support the weight of all that weight from the atmosphere that's above it? As it turns out, the answer is degeneracy pressure, a quantum mechanical quirk of matter under extreme conditions. So astrophysicists have been trying to find a unifying theory between the quantum world and everything else. Here's another little wrench into that attempt. Researchers thought conditions that extreme might be found only in ultra-dense environments like white dwarfs, neutron stars, for example. But as it turns out, Jupiter is providing an example for us. So even when electromagnetic forces are overwhelmed, identical particles like electrons can only be squeezed so tightly together, and as a result, they will not want to be in the same quantum mechanical state. In other words, electrons will never share the same energy level, which means they will keep piling on top of each other, never getting closer, even if you squeeze really, really hard. And if you want to think about it another way, think of the Heisenberg uncertainty principle. If you try to pin down the position of an electron by pushing on it, its velocity can become very large, resulting in a pressure force that resists further squeezing. So you're never going to know its location or its speed at the same time. So the interior of Jupiter is turning out to be quite odd. A soup of protons and electrons, heated to temperatures higher than that of the sun's surface, with pressures a million times stronger than those on Earth, and resulting in interesting quantum behavior. You may recall in a previous video I discussed that Jupiter was an order of magnitude from becoming a star in its own right. We came very close to having a binary system here. Now, if Jupiter had indeed become a star, then chances are the conditions would not have been appropriate for life to have proceeded and evolved on this planet. Just from looking at the typical characteristics, the proximity, and so forth. Either that or life would have to withstand much hotter, more extreme conditions. Be that as it may, I just thought this is a very interesting story that we have a strangely behaving metallic hydrogen that is more of in a liquidy state. It's sort of like what we find metals here on this planet, but the metals we find here behave differently than metallic hydrogen, and it's due to the quantum mechanics that are proceeding. Anyway, I just wanted to bring that with you. I thank you for your continued support, and please tell others of the work that I do here. Thank you for your time. We'll talk soon.